So last time we end up actually with chapter 4 regarding the first law analysis of combustion. We have learned how to calculate, apply the first law of thermodynamic either for open system like the case of gas turbine or diesel engine, or we can consider the case of constant volume combustion or closed system, rigid tank, rigid vessel, how to apply the first law of thermodynamic and how to calculate actually the heat transfer from the system, the heat of combustion, or how we can calculate also the work out of the system. Also, we have learned how to calculate the heating value, and also we talk about the adiabatic flame temperature, which is the maximum temperature of combustion when the combustor is totally insulated or isolated. We don't have any kind of heat transfer. So in this case, the temperature of the product should go, in this case, to the maximum value, or what we call the adiabatic flame temperature. And as we said, the condition for the adiabatic flame temperature for constant pressure combustion or open system is H product equal to H reactant, but actually we don't have the temperature of the product, so we have to do this by trial and error. Like this, also the case of constant volume combustion, we have learned that the condition for the adiabatic flame temperature is U product, or the internal energy of the product is equal to the internal energy of the reactant, and also we don't know the temperature of the product, so we have to do it by trial and error in this case. طيب إن شاء الله يعني today شباب we will get back يعني to the case of internal combustion engine. I think we got in deep for the analysis of the combustion as a theoretical analysis of the combustion system. So let's get back today and slightly back to the internal combustion engine and talk about the engine cycles. Engine cycle شباب, when I talk about cycle, that means actually starting from sucking the fuel plus air during the intake stroke. Then we have compression, then we have expansion until we have actually the exhaust of gases. So this actually from taking the fuel until the exhaust of the gases, we call this is actually one cycle. And then we have to repeat this cycle again in order to generate continuous power. But what are the processes شباب involved in this cycle for gasoline engine and for diesel engine? As a matter of fact, those processes for each cycle are different from the gasoline cycle to the diesel cycle. In case of gasoline engine, mainly the charge actually is fuel plus air. So in the intake stroke, we have fuel plus air. And the combustion in case of gasoline engine usually take place at constant volume, instantaneous combustion at constant volume. And in this case, the system we said actually to work actually on the Otto cycle, in which the combustion take place at constant volume. In case of ideal diesel engine, at the ideal case, we can assume actually that the pressure take place at constant pressure, and in this case, the diesel engine will be working on what's called actually the diesel cycle. In case of the actual diesel engine, actually part of the combustion take place at constant volume, and the remaining part of the combustion process take place at constant pressure. So we have the combination between constant volume and the constant pressure, and in this case, the system is working on what's called the dual cycle. Dual cycle is a kind of combination between Otto cycle and diesel cycle. So inshallah, in this chapter, we'll go through all of these cycles. We'll learn how to calculate the engine efficiency based on actually the different cycle, and we'll compare actually between all of these cycles. But we will start يا شباب with the standard air cycle. Standard air cycle, we assume the working fluid is air. We don't have air plus fuel, just I will assume the working fluid is air. I will assume also the cycle is a closed system. We don't have intake or exhaust port. Just in this case, we have a certain amount of air, and then actually we'll go through expansion and compression. And instead of having combustion, we will have heat addition. Instead of having exhaust stroke, in this case we will have heat rejection. So just we will simplify the cycle for the analysis, for the theoretical analysis, and we will assume all the processes are reversible. We don't have any kind of losses within the system. We'll assume closed system. So in this case, we can calculate the efficiency of the system, the theoretical efficiency, which should be above maximum, or should be greater than the actual value or less than the actual value. Hussein, if I
should be correct.
It will be great. Yes, Alice. In this case, it should be greater, Shabab, because I have assumed actually all processes are reversible. We don't have any kind of losses. We don't have valve. We don't have anything. So just in this case, the efficiency will be actually the maximum value. But what is the benefit, Shabab, from all of these assumptions? So I have just reduced the case we don't have valve, just the air is the working fluid. We don't have combustion, just heat addition, and we have heat rejection instead of the exhaust. So what is the benefit in this case to calculate this efficiency? It will give us indication about what?
To know the upper limit.
Exactly. So in this case, I can get the upper limit of the engine. I can get the maximum efficiency of this engine. Then I can compare it to the actual value. If the actual value is close to the limit, that means actually we have minimum losses in this engine. But if we have big difference between the actual efficiency and the limit, the upper limit, which is the maximum efficiency calculated based on this theoretical cycle, that means in this case the engine should have a bigger amount of losses in this case, and its efficiency should be low. I will talk about all of this air standard cycle, and we'll compare between all of them and see actually which one should have better efficiency under what condition. And inshallah, we'll be moving to talk about the fuel air cycle, which is in this case we will consider the intake and the exhaust valve, and we will consider in this case the working fluid is fuel plus air. And in this case, I will consider also the combustion as well. So the fuel air cycle should be give a clear representation or a better representation of the internal combustion engine, either for gasoline or diesel engine. But in this case, Shabab, still we consider a standard cycle. We consider all processes are reversible. But in this case, this efficiency for the fuel air cycle should be less than the maximum efficiency we obtained using the standard air cycle. Because in this case, in the fuel air cycle, we consider the fuel as a working fluid. We consider intake and the exhaust valve. We consider also the combustion process and the exhaust process. But what is remaining actually, the assumption is still actually for the standard cycle, we consider we don't have any kind of losses. And that also should be a kind of theoretical efficiency. But this theoretical efficiency should be closer to the actual value. Okay? Then we will compare all of this cycle with the actual engine cycle. Then we can see actually how we can get actually indication from the theoretical analysis about the actual engine cycle and the actual performance of this engine. So inshallah, for the air standard cycle, that will be the main subject of this chapter. I will just simplify the cycle. I will assume actually we don't have fuel, just the working fluid is air. I think maybe you have already went through those cycles. Just we don't have combustion, just we have heat addition, and we don't have exhaust, just we have heat rejection, we don't have valve. We assume the system is a closed system. All processes are reversible. We don't have any kind of losses. The specific heat also, specific heat CB and CV should be function of temperature, but we'll assume CB and CV are constant. So in this case, the specific heat ratio P, which is CB over CV, will also be remaining constant in this case. So the three kind of types of cycle we have the Otto cycle, which is applied to the spark ignition engine. Also we have the diesel cycle, which can be applied for the ideal or simplified diesel engine. Or we have the limited pressure, or we call it the dual cycle, which is applied for the actual compression ignition engine. طيب, let's consider here يا شباب those terminology which we have talked before. Those terminology about the engine, I think we have already mentioned, but let's repeat. So here, if we have an engine, and this is the piston, the engine here we have the intake valve, and here we have the exhaust valve, and at the top here either we have a spark plug or we have fuel injector in case of diesel engine, or a spark plug in case of gasoline engine. As we said earlier, the piston is moving up and down between what's called the top dead center, which is the highest point inside the piston, inside the cylinder, and the bottom dead center. And the distance between the top dead center and the bottom dead center, we call it L, which we call it the stroke. So the stroke is the distance between the top dead center and the bottom dead center. And the swept volume, while the piston is moving from the top dead center to the bottom dead center, this swept volume, we call it actually the displacement volume or the stroke volume. And the remaining volume here between the cylinder head and the top dead center, we call it actually as the clearance volume in this case. And the diameter of the piston, we call it the bore. So D we call as actually as the diameter or the bore of the engine. Bore, which is the diameter of the piston. And based on that, we have defined the compression ratio to be the ratio between the cylinder volume, which is V displacement plus V clearance, V displacement plus V clearance divided by the minimum volume, which is the clearance volume in this case. And we say that this compression ratio give us indication about the pressure by the end of the compression stroke. The pressure inside the cylinder by the end of the compression stroke. This pressure should be high if we have actually the compression ratio is high. And to have higher compression ratio, we have to minimize actually the clearance volume of the engine in this case. Okay. But before we move, we talk about this. But before hear what I said, before we move to the air standard cycle, we consider the working fluid as air, which is an ideal gas. So let's talk first about the ideal gas model. Let's revise some concept of the ideal gas model, which most of them actually we have already mentioned, so but just let's revise them again. So the ideal gas model. So the ideal gas. The ideal gas model for combustion. For the ideal gas, we have the ideal gas equation of state, dV is equal to mRT. This is the ideal gas equation, or we can say pressure by volume, mass is equal to number of moles multiplied by molecular weight, R, which is the universal gas constant, divided by the molecular weight. This is by the temperature. So we can say either BV is equal to mRT, or we can say BV is equal to N, R universal, or R bar, which is 8.314 kilojoule per kilomole equal to N R bar multiplied by the temperature. If we took this equation and we divide here by mass, so in this case it will be pressure multiplied by specific volume. This pressure, as I told you earlier, this is the pressure, the absolute pressure. This is the only equation that we have to substitute the pressure by the absolute value, okay, which is equal to gauge pressure plus atmospheric pressure. This is the absolute pressure. And this is the volume, should be in meter cube. But if we divide by mass, the volume by mass will be the specific volume, which should be calculated in meter cube per kilogram. That should equal to RT. So this is a simplified form. Also, we can take this equation and we just divide by the number of moles. Then in this case, we can say pressure multiplied by the molar specific volume will equal to R bar or R universal multiplied by T. This specific volume, V bar, we call it the molar specific volume. Meter cube per kilomole in this case. But if we have an ideal gas, it should undergo a process or a change, let's say from state number 1 up to state number 2. So we can say V1 will equal to mRT1. If we have a closed system, so the mass will be constant. In the analysis of the cycle, engine cycle, we consider a closed system. Okay, based on this assumption for the cycle, the simplified cycle, we assume the system is closed system. So we'll stick here to the closed system, so the mass will be constant. But at state number 2, we can say V2 will equal to mRT2. If I just divide both equations, then we can say for ideal gas, go a process or a change from state 1 to state 2, we can say V1 over T1, V2 over T2. And this is actually for the ideal gas model. But regarding the properties, I will be just going in this part a little bit faster because we have already revised this. The specific heat at constant pressure, CV, is equal to partial differentiation of the enthalpy by temperature at constant pressure. So the properties for ideal gas in the ideal gas model, CV is equal to dH by dt when the pressure is constant. But we said in case of ideal gas, we can treat a gas as an ideal gas under very low pressure, or the density actually is very low. So the intermolecular forces in this case gets very low, so we don't have any molecular order in this case. So the effect of the pressure is vanished in this case. And for the ideal gas, in this case, the properties becomes only function of the temperature. So in this case, we can just remove this partial differentiation. We can convert it to total differentiation. So it will be delta H. Total differentiation will equal to CB delta T. Okay. Like this, also we have CV, specific heat at constant volume, is equal to du by dt at constant when the volume is constant in this case. And also for the ideal gas, we can say delta U will equal to CV delta T. Okay. If you look here, Shabab, I think we have seen this figure before. Usually specific heat at constant temperature and the specific heat at constant volume are function of temperature. Usually they are fourth order equation of the temperature. But usually if we have a small temperature difference, delta T is small, then in this case we can consider the specific heat as constant in this case. But if I need to calculate delta H, so let's do the integration. So it will be integration of CV as function of temperature dt from temperature T1 to temperature T2. Like this, delta U, the change of internal energy for any system undergo any process or change from state 1 to state 2. Delta U also will equal to integration of CV as function of temperature dt from T1 to T2. As I told you, for a small delta T, if we have a small delta T, if delta T is small, that means in this case we can consider in this case specific heat as constant in this case. We can take it the average value. If this is the distribution, we can take the average value, and we can take, as this one is constant, we can take it outside. So in this case, we can say delta H will equal to H2 minus H1 will equal to CV average multiplied by T2 minus T1. And delta U will equal to U2 minus U1 will equal to CV average multiplied by T2 minus T1. For delta H will equal to CV delta T, delta U will equal to CV delta T. Those are the specific properties are calculated in kilojoule per kilogram. If I need to calculate total delta H capital, it will equal to mass multiplied by specific delta H in this case. Unlike this, also we can get the total change of the internal energy. And in this ideal gas model, for the air standard cycle, we consider CV and CB are constant, and in this case the specific heat ratio would be constant as well in this case. So in this model, for the ideal gas model, for the air standard cycle, we consider CV and CV are constant, then we can take them outside the integration. So delta H will equal to CV delta T, and delta U will equal to CV delta T. Is that clear, ya Shabab? Is it clear? Mustafa, is it clear?
Yes.
طيب يعني يا باشا يعني it's a kind of revision يعني we went through. طيب let's remind you with the TDS relation or the Maxwell relation. So يعني this is what we said. TDS relation or the Maxwell relations to calculate actually the change of entropy delta S. For the analysis here, شباب, for the standard air cycle, we assume the system is a closed system. So for a closed system, if we have any closed system, okay, so we can apply the first law of thermodynamic. It will be delta Q in the differential form, the specific form, delta Q minus delta work will equal to delta U in this case. For a closed system, شباب, delta U or the work is equal to the pressure, the force multiplied by distance A. And the force is the pressure by area multiplied by the distance A. Area multiplied by L, which is volume. So the work is equal to the pressure multiplied by volume. Or we can say delta work in this case will equal to integration of BdV in this case. So in case of a closed system, like a piston cylinder device, the pressure in this case we apply pressure force, which is pressure by area, to have a distance movement L. So the work will equal to pressure by volume. And the integration of the work is equal to integration of BdV, how the pressure is varied as function of the volume in this case. So delta work is equal to BdV. And also from the definition of the entropy, based on actually what we call the Clausius. Based on Clausius, you have defined actually entropy delta S is equal to delta Q divided by delta Q divided by P. But by the condition that actually this process is a reversible process. Because in case of irreversible process, we should have some entropy generation due to the irreversibilities. As I told you earlier, if there are any kind of losses within the system, friction losses, heat losses, all of this actually will be absorbed by the molecules and will be dissipated in the random motion of the molecules. And this actually dissipation of energy will appear actually in terms of what we call the entropy generation. Usually this term, Shabab, is almost a positive value because any actual process should result actually in some losses. And all of the losses should appear within the system in the terms of what? In terms of entropy generation. But this is actually in case of actual process. In this analysis of the air standard cycle, we assume actually all processes are reversible. We don't have any kind of losses. So that term will be zero in this case. So the definition based on Clausius, he have defined the entropy delta S is equal to delta Q over T, or we can say delta Q will equal to TdS. So just take this, substitute here, delta O and substitute here, so we can get the first TdS relation. Delta Q will equal to TdS minus BdV, that should equal to delta U. Or we can say TdS will equal to delta U plus BdV. We can just divide by T, so this T will be delta U over T, BdV over T. In case of ideal gas, BV over T, so that will equal to delta U over T plus B over T based on the ideal gas model. BV is equal to RT. So B over T will equal to R over V delta V. Okay. So let's do the integration to calculate delta S. So in this case, we can get an equation. The first equation to calculate delta S, so the change of entropy for a reversible process based on the first TdS relation. We have went through this issue, but I'm just repeating here. So delta S, the change of entropy, will equal to integration of delta U, which is Cv as function of temperature dt, plus R over V. R integration, this integration R is constant, can take it outside, delta V over V, which is ln V2 over V1 in this case. And for the air standard cycle, we consider this term as constant. So Cv is constant, we can take it outside. It will be integration of delta T over T. Then we can say delta S will equal to Cv ln T2 over T1 plus R ln V2 over V1. And this is the first equation we use to calculate the change of entropy if we have actually any system or any ideal gas undergo a process or a change from 1 to 2. This is the equation how to calculate delta S. Type for isentropic process, isentropic. What does it mean, isentropic process? So the entropy, iso means actually equal. Isentropic, so the equal entropy, so entropy is constant. Or we can say delta S is equal to 0. So when I just equate this equation to 0, then in this case it will be ln T2 over T1 will equal to minus R ln V2 over V1. We can just take this Cv inside the ln. It will be T2 over T1 to the power Cv. And we can take the R here. It will be to the power R. When this term is equal to 0, we'll have negative sign. Negative sign will just flip this one. It will be V1 over V2. Then we can say from this, if I equate it to 0, it will be T2 over T1 will equal to V1 over V2 to the power R over Cv. R over Cv, based on the relations that we have proved earlier, this is R over Cv. But we have proved earlier the relation between R, Cv, and Cv. I have proved for you in the preceding chapter, and you know that already. Cv minus Cv, or Cv is equal to Cv plus R, and we have K is the specific heat ratio Cv over Cv. If I took those two relations, I can get Cv will equal to Kr over K minus 1 and CV will equal to R over K minus 1. So يعني from those two relation, I can get those two relation. Okay? 5R over CV, that means it will equal to K minus 1. So here we can just remove this one, it will be K minus 1. So if we have an isentropic process, and this is the first relation here, we can have the isentropic relation T2 over T1 will equal to V1 over V2 to the power R over CV. Like this, شباب, we can get another TdS relation. By definition, we have insol V is equal to U plus BV, or we can say delta H will equal to delta U plus BdV plus VdB. We have two variables. Type we have delta U plus BdV from the first TdS relation. This term delta U plus BdV is equal to TdS from the relations that we just have proved right now. Okay, equal to delta U plus TdS. So this term is equal to TdS. So we can get another relation for TdS. TdS will equal to delta H minus VdV. And then we have another relation for delta S. Divide by T and delta H will equal to CB dt. Then in this case, substitute by the ideal gas equation, we can get another relation to calculate delta S. This other relation, this relation is based on the specific heat at constant pressure. So it will be delta S will equal to CB ln T2 over T1 minus R ln V2 over V1. If it is equal to 0, then I can get a relation between temperature and the pressure for isentropic process. T2 over T1 will equal to V2 over V1 to the power K minus 1 over K. Okay, so we can just, and we have from the first TdS relation, we can say T2 over T1 is equal to V1 over V2 to the power K minus 1. Now here we have the same left-hand side. Then those two terms are equal in this case. And those are what we call the isentropic relation. And I think you are familiar with, if we have an isentropic process, because this will be, we will have two processes, isentropic processes, in case of a standard air cycle. If we have an isentropic process from state 1 to state 2, we can just use actually based on the constant specific heat analysis. As we said in the standard air cycle, we will consider the specific heat and at constant pressure and the specific heat at constant volume are constant. So based on the constant specific heat analysis, we can develop actually the isentropic relation T2 over T1 will equal to B2 over B1 to the power K minus 1 over K, and T2 over T1 will equal to V1 over V2 to the power K minus 1. Okay, and those are what we call the isentropic relation. So let's apply this ideal gas model to the air standard Otto cycle, which is a representation of the gasoline engine. Okay, I will just take those relations, and then I will apply them directly right now to the case of air standard Otto cycle, which we can apply, or it can represent actually the cycle, one cycle for a gasoline engine. Let's look at this cycle and see how we can represent it on the PV diagram and see the different processes. If you look here, Shabab, for this cycle, this is the actual engine cycle. We have fuel is injected plus air in the gasoline engine. Then we have the intake stroke or the suction stroke, followed by the compression stroke, compressioning the air plus fuel. Then we'll have the ignition will start, and we have the expansion of the power stroke. And at the end, the piston will be moving up, and we'll have the exhaust stroke, and the exhaust valve will be opening to exhaust the gas. If you look at this process, Shabab, on the PV diagram, this is first of all at the start of the compression stroke, starting from the bottom dead center. After the intake stroke, the piston move from the top dead center to the bottom dead center. And here is the point, Shabab. So at the beginning of the compression stroke, the intake valve will close. And in this case, the gases will be compressed during the compression stroke. Before the piston approaches the top dead center, we'll have the ignition. And in this case, the pressure will be raised inside the cylinder. But as you can see, Shabab, for the actual cycle, in this case, the combustion process is not at constant volume. But we can, in the Otto cycle, standard cycle, we can represent this one as actually as constant volume. but this is an assumption, okay? So then we'll have the combustion, and then the piston will be moving down toward the bottom dead center during the power stroke or the expansion stroke. Usually we open the exhaust valve before the end of the expansion stroke to make sure actually that the pressure value is high so that we can scavenge all of the exhaust gases inside the engine. So the exhaust stroke will be beginning, and usually, and while the piston is moving from the bottom dead center to the top dead center, it should be compression. So the pressure should be increased, but actually the exhaust valve is open. So in this case, the pressure is trying to increase due to the piston movement, but the gases are leaving, so almost the pressure remains constant. But the pressure during the exhaust stroke is higher than the atmospheric pressure, and it is higher than the pressure in the intake stroke. Pressure in the exhaust is higher to be able actually to just exhaust all of the gases or scavenge all of the gases. At the end of the exhaust stroke, in this case, the exhaust valve will close and the intake valve will open, and the piston will be moving down. Moving down, it will create a vacuum inside the cylinder. So the pressure will get down, and the intake charge is coming in, and then actually we have until the piston reaches the bottom dead center, and again we can repeat this cycle. Okay. This is the actual cycle in which we have fuel plus air, we have combustion, we have intake air, intake valve, and we have exhaust valve. And this is the representation of the actual cycle. But this actual cycle is a little bit complicated to be analyzed. So let's consider the standard actually Otto cycle. In the standard Otto cycle here, I will assume the working fluid is just air. We don't have fuel. And we will assume actually we don't have valve. So valve means the system is open. Intake valve and exhaust valve. No, I will assume we don't have valve, so the system is closed. Just we have a certain amount of air. Then we will compress the air, and at the end of the compression, at the top dead center, I will start heat addition. We don't have combustion, just we have external heat addition. Then at constant volume, then we will have the expansion stroke, and at the end actually we'll have heat rejection at constant volume in this case. And this is the representation of the cycle, or the ideal cycle, ideal Otto cycle on the PV diagram. So let's look at those processes on the PV diagram for the Otto cycle. So the representation of the Otto cycle, which is applied for what? Gasoline or diesel engine? Which is applied, can represent actually the cycle yes, the cycle for the gasoline engine. So Hussein, are you following? Hussein? Abdullah? Rida Abdullah? Saeed?
Yes, doctor.
So brother, please follow. So here, is a representation of the cycle on the PV diagram. Let's say this is the line representing the top dead center, and the volume in this case, when the piston at the top dead center is equal to the clearance volume. And this line, let's say this line representing the bottom dead center, and the volume between the top dead center and the bottom dead center, we call it the displacement volume. Okay. And let's say the engine is starting from point 1 here at the beginning actually of the compression stroke. The piston is at the bottom dead center, and in this case we'll start the compression process. So the first process is compression from state 1 to state 2. So process from 1 to 2 is actually, for this process to be reversible. To be actually reversible without any kind of losses, so the process is reversible, and also don't have any kind of losses, and also the process actually is adiabatic in this case. Reversible and adiabatic, that mean actually the compression process is an isentropic process. So process from 1 to 2 is isentropic compression process, in which the entropy will be constant, and delta S, or the change of entropy delta S, should equal to 0 in this case. Isentropic process means that this process is reversible, plus this process is also adiabatic. So we don't have heat transfer. Reversible and adiabatic, that means actually the entropy will be constant, because delta S is equal to delta Q over T. Okay. it should be plus the entropy generation due to the irreversibilities. If it is reversible, so we don't have entropy generation, this term is 0. But we should have a change of the entropy if we have heat transfer. So in this case, if the heat transfer is 0, the system is adiabatic, so reversible plus adiabatic, that means the process is isentropic, or delta S in this case should equal to 0 in this case. And at the end, actually, of the compression stroke, when the piston approaches the top dead center, so the process from 2 to 3 will be actually the constant volume heat addition. So process from 2 to 3 is a constant volume heat addition process. So in this case, this process actually, the heat will be added at constant volume in this case. And this is actually the second process which can represent this heat addition process under constant volume. It can represent the actual case actually of the spark ignition engine. We can just assume here after the ignition that the combustion, it is almost constant volume. So in this case, we can assume actually the heat is added in this case of the combustion occur under constant volume. In this case, this is the case of the gasoline engine. And then after the heat addition, then the piston will be moving down. Then we will have actually the expansion stroke. So compression from 1 to 2, heat addition from 2 to 3, and then we'll have expansion process from process actually 3 up to process 4. So process from 3 to 4. This process should have to be reversible without any losses, should be reversible plus adiabatic. So we should have isentropic expansion process. So in this case, entropy will equal to constant, or in this case, delta S will equal to 0. At the end of the expansion stroke, we should have the exhaust stroke. We can represent in this case the exhaust stroke by the constant volume heat rejection from process 4 to 1. So in this case, the heat, and this should simulate the case when we just open the exhaust valve. So the exhaust gases will be leaving under high pressure, high temperature. So this is a kind of heat rejection process. But usually in gasoline engine, we do have a separate exhaust stroke. So the piston should be moving after the process from 4 to 1, which includes the heat rejection. In this case, the piston should be moving actually from state 1 until it reaches the top dead center. So we can represent this case here as constant pressure exhaust stroke. But we don't have any kind of heat addition or heat rejection. This is for the ideal cycle. And also we assume in the ideal cycle that the intake stroke will take place at the same actually exhaust pressure. So the piston will be moving back here. Let's say this is state number 5. So it will go from 1 to 5 without heat addition or heat rejection at the same pressure, so that we can have exhaust stroke. Then the piston will be moving from 5 to 1, and that will be, so from 1 to 5, this is the exhaust, and from 5 to 1, this is actually the intake stroke. We assume both of them occur at the same pressure. And we will get back actually to the same as point 1 in this case. Okay? But in case of closed system, we said the work. So the last process first is the process actually from 4 to 1, which is constant volume heat rejection. So the heat will be rejected under constant volume instantaneously when the exhaust valve open in this case. But in this cycle, we assume that we don't have exhaust valve. And then the piston will be moving from 1 to 5, which is the exhaust, and from actually 5 to 1, which is the intake. But we assume in this case, for the standard Otto cycle, that the system is closed. We don't have intake valve, we don't have exhaust valve in this case. And for a closed system, we have defined the pressure is equal to integration of BdV. But let's look here on the PV diagram. If we have a process from a state, let's say 1 to 2. The area under the curve here is represented by what? Under the PV diagram. If I took an element here, element of the area, this element has width. Yes?
Represent the work.
Exactly, in this case, but just I prove it. So this element has a width delta V, and it has a height here B. So this element area, we call it delta area, will equal to BdV. If I integrate to calculate the whole area under the curve, so the area under the curve will equal to integration of BdV. Integration of BdV is representing the work. So the area under the curve on the BV diagram represents the work. طيب this work يا شباب during the compression. During the compression actually the work is coming from the crankshaft to drive the piston. So this is actually the work is applied on the system. So that should be a negative work, which is a compression work. And the area in this case is represented by the area under this curve, which should be negative work in this case, negative value. But in the expansion stroke, in the expansion we have combustion, and the combustion will press the piston down. So in this case, this work is generated by the system. So it should be positive value. So the work in this case is positive. And it should be represented by the area under the curve, which is this area. Okay, the total area. But this area green is positive in the expansion, and under the process from 1 to 2 is negative. That means the net work actually done is equal to what, Shabab? Net work done for this cycle should be represented by the area contained actually by all processes on the BV diagram. So this, Shabab, represents the net work of this cycle, which is equal to the work of the expansion minus the work of the compression, in this case. Okay, this cycle, Shabab, also can be represented. So this cycle can be represented also on the TS diagram. We can represent the same 4 processes for the air standard cycle on the temperature entropy diagram. So process from 1 to 2 is isentropic compression. So let's say this is point 1. From 1 to 2 is isentropic compression. So it will be just a vertical line from process 1 to 2. Then from 2 to 3, this is actually the constant volume heat addition. So heat added on the constant volume. So this is volume, line representing volume is constant. This case S for the entropy is constant. And in this case, we have the compression process for the isentropic process from 1 to 2. Then constant volume heat addition from 2 to 3. And then from 3 to 4, we'll have expansion. We have expansion work, isentropic expansion. So entropy is constant from 3 to 4. And from 4 to 1, again, it will be actually heat rejection. Q is rejected, should be negative value. And also constant volume. So from 4 to 1 is constant volume. But the area contained here is not by the cycle on the TS diagram. This area is represented by what?
Net heat.
Sorry, Hussein? Hussein? You said something?
The net heat.
Exactly. So this area, Shabab, is represented by the heat transfer, net heat transfer. Okay? So the heat added from 2 to 3, this is a positive, and the heat is rejected from 4 to 1, that should be negative. And the difference should be actually the net heat transfer. As we said, Shabab, on the TS diagram, we said the relation between the entropy and the heat transfer, that delta S is equal to delta Q over T. We assume for the reversible process. Or delta Q is equal to TdS. Or if we integrate, so the total heat transfer should equal to integration of TdS. Integration of TdS like the integration on the VdV. So it will equal to the heat transfer in this case on the TS diagram. So the area contained by the cycle on the TS diagram should equal to the net heat transfer. Okay? But if the system, Shabab, is working on a cycle, working on a cycle means what? The final energy, we are starting from a given point and do so for a cycle. We start actually from a given point, do whatever the processes I'm doing, and get back to the same point. So the initial point is the same as the final point, like this cycle. I started from point 1, compression, 2 to 3, 1 to 2, then 2 to 3, followed by 3 to 4, and then I have to get back to the same point, point 1. And then I have to repeat this cycle in order to generate actually continuous work. So I start from point 1, do whatever the processes, and get back to the same point. So the change of energy of the system, which is the final energy minus the initial energy, should equal to what? Should equal to 0. And if we apply the first law of thermodynamic for a closed system, Q minus work equal to delta E for the system. Delta E is equal to 0 as the system is working on a cycle. So for a cycle, we should have Q net is the same as what, ya shabab? So this term should equal to 0. So Q net should equal to work net. Q net is the work of the expansion minus work of compression, and the Q net is the heat added minus the heat released. And this is a shabab for any system working on a cycle. Okay, is that clear, ya shabab?
But Doctor, this is not taking account for the efficiency.
Yes, so in this case, just theoretically, we assume actually that the net heat transfer is equal to the net heat added in this case. Okay, but this has nothing to do, ya shabab, with the efficiency. This is the concept of the operation. Okay, now this is something, ya shabab, this is the basic for a cycle. For any cycle, I have to repeat and get back to the same point. So the change of energy should equal to 0. Energy can transfer for a closed system in terms of heat transfer and work. That means Q net should equal to work net. So this area should equal to work this area. Yes, Ali?
Yeah, I got it.
So, but this is, I will talk about the efficiency right now, about all of these processes, and calculate the efficiency for a standard Otto cycle, which can be applied for gasoline engines. That means this efficiency we can use to calculate the efficiency of a gasoline engine in this case. Okay, so let's consider process by process and see. So for process from 1 to 2, this is isentropic compression. So delta S should equal to 0. And we said isentropic is reversible. The process is reversible plus adiabatic. Adiabatic means the heat transfer is equal to 0. But we assume, ya shabab, for all of this analysis, for the all standard cycle, that the system is closed system. Closed system, so the first law will be Q minus 4, as we learned from the last chapter, will equal to delta U, the change of internal energy. Okay, heat transfer here is 0, and the compression work in this case, ya shabab, this is positive or negative work? This is the compression work that should be negative. So based on the first law of thermodynamic, Q and the heat transfer, Q and work are directional quantity. I should substitute with its sign. So it is negative sign. So we have negative, and this one is negative. So it will be positive. So the work will equal to delta U, which is equal to M multiplied by specific exchange of internal energy U2 minus U1. Or we can say work over mass, which we call it actually W small, which is the specific work divided by mass will equal to delta U. And delta U, based on the ideal gas model, we said for ideal gas it will equal to CV T2 minus T1. And this is the work, the compression work. We call it, this is the compression, will equal to CV multiplied by T2 minus T1. And during this compression process, shabab, we can say B1 V1 over T1 will equal to B2 V2 over T2. And this process is isentropic. We can apply the isentropic relation. We can say T2 over T1 will equal to V1 over V2 to the power K minus 1. This is the isentropic relation that we have proved for an isentropic process. T2 over T1 will equal to V1 over V2 to the power K minus 1. So what about the ratio V1 over V2, ya shabab, is equal to what? When the piston is here, at the bottom dead center. So the volume V1 will equal to what? The displacement volume between the top dead center and the bottom dead center plus the clearance volume. So that should be the cylinder volume. This is V1. Top V2 will equal to the clearance volume. So the ratio between the cylinder volume at 1 divided by the clearance volume at 2. So that should be representing what, Ashibal? This is representing what?
Compression rate. The compression ratio.
The compression ratio. So that should equal to R to the power K minus 1. And this relation is very important. T2 over T1 will equal to R, which is the compression ratio of the engine, to the power K minus 1. This is for the first process from 1 to 2. we got this relation, the compression work is equal to CV delta T, and we got the relation between temperature and the compression ratio through the volume, this relation. Type process from 2 to 3. 2 to 3 is constant volume heat addition, so heat is added. That means it is positive, should have positive sign. And this is constant volume. We said the work is equal to integration of BdV. If the volume is constant, so that means the work is equal to 0 in this case. And the work is represented by the area under the curve on the BV diagram. This is just a vertical line, so the area is 0. So the work in this case is 0. Apply the first law of thermodynamic, U minus work will equal to delta U. Work is 0 as the volume is constant. Heat transfer has positive sign, so Q in this case, or let's say Q over M, which is a specific heat transfer Q small, will equal to CV multiplied by T3 minus T2. But if the volume is constant, we can apply this relation, but between point 2 and point 3, but the volume will be constant. So we can say B3 over B2 will equal to T3 over T2, as the volume is constant in this case. Can just reduce the ideal gas equation to this one. But this is for process from 2 to 3. We have calculated in this case Q added will equal to CV multiplied by T3 minus T2. Okay, like for process from 3 to 4, isentropic expansion, delta S is equal to 0. Isentropic means it is adiabatic, so Q is 0, so Q minus work is equal to delta U. Q is 0. Work is expansion, so it should have positive sign, but we have negative sign here. So the work will equal to minus work over mass, which is a specific work, will equal to minus delta U. So it will equal to CV. Delta U from 3 to 4, we have negative sign, so it will be 3 minus 4. T3 minus T4. And this is the work in this case from 3 to 4. But we have isentropic relation from 3 to 4. That means T4 over T3 can apply the isentropic relation will equal to V3 over V4 to the power K minus 1. V3, which is V clearance. V4, which is the cylinder volume. So it should equal to 1 over the compression ratio. So that should equal to 1 over R to the power K minus 1. And this is for the process from 3 to 4. So Shabab, this is 1 to 2. This is 2 to 3. And this 2 from 3 to 4. Let's remove this and get the last process. So the last process from 4 to 1. From 4 to 1, this is constant volume heat rejection. So Q is rejected. That means it is negative sign. And the volume is constant. So the work will equal to integration of BdV will equal to 0. Q minus work equal to 0. Delta U, work is 0. So Q, which has negative sign, because it is rejected, will equal to delta U. Divide by M. So that should equal to, and take the negative sign here to the other side. So it will be CV instead of 1 minus 4. So it will be T4 minus T1. Okay. And this is the reject, the heat reject. Okay. We call it a specific heat. Q small. Okay. And the same from 4 to 1. This is constant volume. Then we can say T4 over T1 will equal to B4 over B1. And this is for the last process, from 4 to 1. Now we have all relation. This is the heat rejected. And this is the heat added. This is the compression work. And where is the expansion work? From 3 to 4. This is the expansion work from 3 to 4. I just removed it. So the expansion work will equal to CV multiplied by T3 minus T4. This is the expansion. But we said for a cycle, Q net is the same as work net. Like to calculate the efficiency of the cycle, so let's remove this. The efficiency of the cycle will equal to what if you the work out
over the Q.
So exactly. So the work added, work net divided by Q added. And for this cycle, we have Q net is the same as work net. Q net, which is Q added minus Q rejected, will equal to the expansion work minus the compression work. And the efficiency, thermal efficiency of the Otto cycle, which can represent the case of a spark ignition engine for the standard cycle, will equal to the net work out, work net, divided by the heat added in this case. Okay, or we can divide by the mass up and down. We said this is a closed system, so the mass will be constant. Then it will equal to Q net, specific value. We have work net is the same as Q net, so we can substitute Q net divided by heat added, and the Q net is equal to Q added minus Q rejected divided by Q added, so it will be equal to 1 minus Q rejected divided by Q added. The rejected heat from 4 to 1 will equal to CV T4 minus T1, and the heat added, which is actually for the process from 2 to 3, so the heat will equal to CV T3 minus T2, and that should be the efficiency of the Otto cycle. Okay, but I need from all of this which relation? I need this relation. This relation and this flow relation. Here. So we have proved that T2 over T1 will equal to V1 over V2 to the power K minus 1, which is equal to R to the power K minus 1. Here we have T4 over T3 is the same as 1 over R to the power K minus 1. But let's take this efficiency for the Otto cycle will equal to 1 minus CV will go with CV. We can take T1 as common, it will be T1, and we'll have T4 over T1 minus 1. And here we can take T2, will be T3 over T2 minus 1. Okay? Type T4 over T1 and T3 over T2. This is T4 over T3 is equal to 1 over R to the power K minus 1. Or we can say T3, sorry, this is T2 over T1 will equal to R T2 over T1 will equal to, or we can say T1 over T2 will equal to 1 over R to the power K minus 1, which is the same as T4 over T3. T4 over T3 is equal to 1 over R to the power K minus 1. So from here, T2 over T1 will equal to, or T1 over T2 will equal to 1 over R to the power K minus 1. And it is the same as T4 over T3, which is the same 1 over R to the power K minus 1. But from this relation, can we say T4 over T1 is the same as T3 over T2? So T4 over T1 is the same as T3 over T2. So T4 over T1 is the same as T3 over T2. So the whole term here will go with this term here. So that should equal to 1 minus T1 over T2, and T1 over T2 is equal to 1 over the compression ratio to the power K minus 1. And this is the efficiency the theoretical efficiency of the Otto cycle in this case, and it can represent the case of gasoline engine. Is that clear يا شباب؟